All right, here's a very interesting project. Um, Essentially, where you're doing stochastic resonance with the hysteresis built into almost any digital input pin. Um, if we configure that, we can open the data sheet right from here, and we can see what do we have for hysteresis. This parameter, it's always on. Um, and somewhere it'll tell you what it is. Although it's not the differential one. Um, so 0.05 times VDD, so 0.05 times around 5. Um, anyway, it can be measured. So really, you just have an input pin and an output pin. Right? We can configure it. It's really just digital input, hardware connection, high impedance, initial drive state high, and the output, digital output, hardware connection. That's we can leave it in strong drive. I used whatever the template was. Now it talks about an error here, but this was running. The pins, I chose pin 1 and 2 to be P10 and P11 on the 43 kit. Just I liked better where it was on the board. Maybe I could have put a picture to the circuit in the comments, but really it's the PSOC kit used as a function generator, or the PSOC programmer, excuse me, and then the kit, it's really just wired through. The excited tone is because it worked, and it's kind of interesting. This is it working. But how do you know you have a Schmidt trigger on the input pin? Well, you would go to a triangle input, right? And then bring the amplitude all the way up. And then I bring the offset down. And really, you would just view XY mode, and you can see that there's a hysteresis width, which one could measure, right? Which is about as easy as it gets. Sorry, I guess I'm geeking out. So we can zoom in on it a little bit, but basically, the trip point high to low is different than the trip point low to high. Now, how can we see if it's acting like stochastic resonance? Well, let's just turn that off. And I think I'd like to kind of zoom in just a little bit. And that goes a little bit off. Okay. Anyway, and I'm just going to zoom in just a little bit so I can see what I'm doing at first. All right, so now it's definitely, there's hysteresis. When there's hysteresis, well, actually, you can stop right there. There will be stochastic resonance. But now what I want to do is figure out the right amount of noise. And that can take a little bit of doing. What I like to do is select noise, right? And then I'm just going to raise it to about where it was before I had it working. And if I can see the auto measurements, all right, I think it could have been working at 420. And then I just raise the offset, and the output will eventually start Okay. So the output just went high, and see how it'll go low, but it doesn't quite trip in the same spot. So the noise amplitude is too small, right? So in fact, it's sometimes easier just to make a bigger noise, okay, and then get it working. I'm gonna zoom out or zoom in a little bit, right? So now, I just moved this up until I got it working. I'm trying to get the average of the output to be about the average of the swing, which the peak to peak on the output is 4.71, so around 2.3. I'd like to see the average, and so I'll adjust the offset to try to make that happen. But it is bouncing around quite a bit, right? Then once it's working, right, you can come back and lower the input noise until you start to see it to work. And now it's kind of triggering all over the place. I'm just going to zoom, get more data. The average is a little bit low, so I just raise the offset a little bit. And yeah, it's a noisy measurement, so this average is bouncing around, right? And it won't be exactly halfway because digitization errors. It's only 8 bits, but still, it's quite clever system. So it seems like 4140 is about right. Then I can even go back now and keep lowering the noise input until it completely stops working, right? That might not be, well, what we do is we take like 20 measurements of this and to get the first, that full width half maximum plot, all right? So this would be our starting point, right? I forget what the spectrum analyzer will. So this is just our noise spectrum, right? And the full width half maximum of that should increase as I increase the noise. And it's a little hard to tell. You do need that Python package to analyze it. Oh wait, sorry, that was the input. We really want to be looking at the output, right? So there's no noise coming through, and then as I increase it, hopefully one should be able to tell that it's moving. Unfortunately, what's happening is as I increase it, I might have to adjust this each time to get it halfway. And so if you're looking at your full width half maximum plot, for example, where is it? Okay. So sometimes that full width half maximum versus 1 over the amplitude of the noise can jump around a bit. And what causes that is each time you take one measurement at a different noise, you've got to adjust the amplitude to get a higher noise, right? Auto measurements, right? So our peak to peak of the noise, 1.73, the average of the output is up at 4, so I have to adjust the DC offset to try to get that close to the middle again. Okay. And then you would do the process where you just take 20 measurements and then the software stitches it together. But I've seen this on many different systems, and even though I haven't done a full width half maximum plot of this, I know that there will be stochastic resonance. The only thing that would need to be done to detect a signal is you'd have to have a noise source and add the sine wave to it, which could be done externally to the PSOC. This won't add noise. This function generator won't add noise to your sine wave, but I think other commercial ones will. Or you just build an op-amp circuit. That'll do it for you, which you could even do with the PSOC. But anyway, to demonstrate that it will be a stochastic resonance, you would just use this and plot 1 over the RMS and of the noise and extract the line. So anyway, it's pretty exciting.